So welcome in everybody to our first N3AS seminar of this lovely new year. Welcome back everybody. And we're very excited to start off our seminar series this year by hearing from Joachim Kopp from CERN and Gutenberg University in Mainz. And today he'll be telling us about neutrinos from neutron stars. So please, whenever you're ready, take it away.
Okay, well, thanks a lot for the invitation. Happy New Year, everyone. It's my great pleasure to be giving this talk about a topic which I should say is relatively new for me. So please be critical and don't shy away from giving your honest opinion on the things I'm going to talk about, which is neutrinos from neutron stars. So that falls into the broad category of neutrino astrophysics, which is already a fairly established topic. So neutrinos act as astrophysical messengers in many different contexts. This has started in the early days with solar neutrinos, which have taught us a lot about stellar evolution, in particular about the inner workings of our own star. Supernova neutrinos, we've only observed them once in 1987, but that one supernova has really provided a treasure trove of information on the one hand, on what's happening during the death of a massive star, nucleosynthesis, matter under extreme conditions, and so on and so forth. And of course, we hope very much that in the not too distant future, we'll catch another supernova in the neutrino channel. And then, of course, we'll be able to learn much, much more from it. Nowadays, high-energy astrophysical neutrinos are one of the latest kids on the block, which are teaching us more and more about the origin of cosmic rays and about extreme astrophysical environments like AGNs, blazars, well, and our own Milky Way since recently. Cosmology, we all know that neutrinos play a very important role in the early universe, affecting structure formation and many other aspects of the early universe, BBN, and so on. Now, a topic that is relatively new and which I want to talk about today is neutrinos from neutron stars. This encompasses, on the one hand, the well-known cooling channels of neutron stars. So neutron stars, for the first order million years of their life, lose most of their energy in neutrinos. But then I'd also like to focus on two topics that have not been discussed in the literature before, which is muon decays in neutron stars and neutrinos from so-called common envelope events. And I'm going to explain in more detail what that is in the course of the talk. Okay, so let's start with neutron stars. Here's a very rough sketch of what a neutron star looks like. Basically, the matter gets more and more exotic as we move inside from large radii. So at the very outer edge of the neutron star, it's relatively standard matter consisting of helium, hydrogen, carbon, basically atoms and ions. Then the crust of the neutron star contains ions and electrons, and then towards the inside, there's more and more free neutrons into which those ions are embedded. The core of the neutron star consists of superfluid neutrons, superconducting protons, electrons, and muons. And the very inner core, we are not entirely sure what it consists about, and there is probably hyperons in there, and maybe even some much more exotic forms of matter, like strange matter, for instance. We really don't know that much about the very inner core of neutron stars. And that's why it's interesting, because there's something to be learned there. Now, neutron stars are born in the explosions of massive stars, so in supernova explosions. And since the temperature during a supernova is extremely high, the neutron stars start their lives at a very, very high temperature, of order tens of MeV. Then they rapidly cool down. This is shown here in this diagram on the right-hand side, which sets out at about 0.1 years of age and goes all the way up to 100 million years. And you can see these characteristic steps in the cooling curve, all of which indicate different physical regimes in the cooling. So the most important cooling stage, which is the one here where most of the data points are located, this is the epoch where neutrinos are still the dominant cooling channel. As you can see, the theoretical predictions that are shown in the background for different equations of state, they vary wildly. depending on, well, first of all, the equation of state, but also the mass of the neutron star and other properties play an important role there. And this is really where much of the uncertainty in our understanding of neutron stars is coming from. At very late times, so neutron stars that are older than, say, 1 million years or so, they are already fairly cold. And at that point, this is then when neutrino cooling becomes less efficient, and most of the cooling is via most of the remaining cooling is via photon radiation from the surface. But that's not a regime that we'll be focusing that much on in this talk. Okay, so how does this cooling happen? Perhaps the simplest process is the so-called direct Urca process, which is basically these two diagrams here. The first one is just standard neutron decay, a neutron converting to a proton, charged lepton, and an antineutrino. But of course, this is not just a regular free neutron decay, because all of this is happening inside a degenerate neutron Fermi gas, proton Fermi gas, and lepton Fermi gas. So the kinematics are very, very different from standard free neutron decay. And in addition to this process, there's also the, well, I don't want to say inverse process, but let's say the process that starts with a proton and a charged lepton going to a neutron. Now, if we imagine the star being in equilibrium, then those two processes, they balance each other. So neutrons get converted into protons at the same rate at which protons get converted into neutrons. But every time one of these reactions happens, a neutrino or antineutrino is emitted, and this is how the star loses its energy. Now, that's a very simple process. However, it's only relevant in the very heaviest neutron stars, in the very cores of the heaviest neutron stars, and that's because of the degeneracy of the fermion gases. This process only works when the neutron Fermi momentum is less than the proton Fermi momentum plus the lepton Fermi momentum. That's basically the precondition for this process to have any phase space at all. So even though it's very simple, this is actually not the most relevant process. The most relevant process is this one, the so-called modified Urca process, which is the direct Urca process plus an extra spectator nucleon that couples to the nucleon that's undergoing the transition, for instance, via pion exchange. And because of the extra nucleon, there's an extra partner that can absorb momentum. And that ensures that there is always, in all neutron stars, in all regimes, there's always kinematic configurations where this is allowed. So this is the dominant cooling channel for neutron stars during the first or the million years of their lives. What I've skipped over a bit so far is I've always talked about charged leptons. Now, when I say charged lepton, I mean an electron or a muon, not just an electron. So that will be very important for us in this talk, that neutron stars, the negative charge in neutron stars is not only carried by electrons, but a large fraction of it is in fact carried by muons. This is shown here for one specific equation of state. The horizontal axis here is the number density of nucleons inside the star, and the vertical axis is basically the fraction of that particle density carried by different species. So if you look here at the white curve, obviously the most abundant species is neutrons, because, well, that's what gives the neutron star its name. But then there's also a significant number of protons, electrons, and, well, muons. And at higher densities, then also hyperons play a very important role. The main reason why there are so many muons in a neutron star is because it's just thermodynamically advantageous for the neutron star to have muons in its core. And that's because, well, the electrons form a degenerate Fermi gas. So once there are so many electrons that the electron Fermi energy is larger than the muon mass, then it's energetically favorable for the star to make muons, as opposed to adding more electrons, because adding more electrons costs more and more and more energy. So it may be advantageous to just make a muon instead. And that's in fact what happens. And that's why over a wide range of densities, there is an abundance of muons that's almost as large as the abundance of electrons. At higher densities, then there's hyperons that can also carry a negative charge, and then the muons and the electrons as well become less important. Once again, this is for one specific equation of state. This picture looks somewhat different for different equations of state. For instance, for some of them, the muon and electron abundance remains large even at the highest densities. But the take-home message from this slide is, well, there is a lot of muons in neutron stars, and they can do interesting things. Now, most of the time when we talk about neutron stars, we think about neutron stars in chemical equilibrium, which basically means that the forward and backward Urker reactions exactly balance each other. So in that case, the number densities of the particles in the star are stable, and the star is just slowly losing energy into neutrino radiation. Now, what my collaborator Toby Opferkuch and I have started thinking about is what happens when a neutron star is not in thermal equilibrium. And there's a number of reasons why neutron stars may experience slight deviations from thermal equilibrium. Here's a breakdown of the ones we could think of. The first one is spin down, for instance, due to electromagnetic energy loss. You know that many neutron stars have very complicated electromagnetic fields around them. And the interaction of the star with the field and the radiation that comes from the field slowly extracts rotational energy from the star. So fast rotating neutron stars, they tend to slow down their rotational frequency over time. Now, when a star rotates quickly, it's not entirely spherical. It is a little bit oblate. So it's a little bit wider at the equator than at the poles. And then as it slows down, it becomes more and more spherical. And this has a very slight influence on its central density. And as we've seen before, the central density has an impact on the particle abundances in the star. So if a star spins down, there is a certain pressure for it, a chemical pressure for it to change the particle abundances in its core. And then the star has to figure out how to do that, how to respond to that, and how to go back into equilibrium. A similar thing happens when a star accretes material. Accretion basically means the star gets heavier and heavier. And for heavier neutron stars, the central density is also different from lighter neutron stars. And so as the star accretes more and more material, its central density changes, the relative particle abundances change, and therefore the star has to respond by creating or destroying particles. A third possibility how a neutron star can deviate from equilibrium is the expulsion of magnetic fields. So most neutron stars are born with relatively large magnetic fields, and some are born with outright enormous magnetic fields. So a typical magnetar can have a magnetic field of up to 10 to the 15 Gauss at its surface, and perhaps even larger at its core. Now, it turns out that these magnetic fields tend to be pushed out of the star over astrophysical timescales. There's a lot of debate in the literature of what those timescales are, maybe 1 million years, maybe 1 billion years. But typically what people find is that after a while, the magnetic field in the core of the star gets reduced. Now, whether or not there's a large magnetic field in the core also has an impact on the particle abundances. Basically because when there's a large magnetic field, there's Landau quantization. So all the charged particle states are Landau quantized, and the density of the Landau levels is different from the density of quantum states available in non-magnetic matter. And therefore, once again, the central densities depend on the magnetic field, and the star has to somehow respond. Finally, tidal deformation. So when a star is, for instance, in a binary system, it experiences tidal forces. And these tidal forces, they also tend to deform the star. So in the same way as rotation tends to deform the star, tidal effects do the same. And there's probably additional mechanisms that we haven't thought about. But what's common to all of these processes is that they lead to a change in the equilibrium abundance of particles, and the star needs to react. And the way it typically does this is via out of equilibrium Urker processes. So now the equality from here does no longer hold. So maybe the forward reaction is faster, or maybe the backward reaction is faster. And what we've done is we've calculated these rates, and here is the result. It's quite a busy plot, so let me walk you through it. What we show here is specifically for muons. So somehow we came to this whole topic by being interested in the muon population of a neutron star. So this is shown as a function of the muon Fermi momentum relative to its equilibrium Fermi momentum, but it's similar for deviations for electrons. So the vertical white line here, that is the equilibrium configuration. That's where the actual Fermi momentum of the muons is where it should be for an equilibrium neutron star. And then towards the left and towards the right, we show possible deviations from that equilibrium configuration. The vertical axis shows the rate of various different processes. And please note that this vertical axis goes over more than 30 orders of magnitude. So, for instance, let's focus here on the turquoise line and this dark yellow line here, which is the modified Urca neutrino production, muon production and modified Urca muon absorption processes. So those are the two processes I've shown in the previous slide. And as you can see, when the star goes away from equilibrium, then very quickly, even for tiny deviations, those rates, they change dramatically. They change by many, many, many orders of magnitude. And that's because the quantity that's shown here on the horizontal axis, it essentially appears inside an exponential. And so that means the star will be quite efficient at responding. The same is also true for direct Urca, which is the white and orange lines here. Once again, if direct Urca is allowed, then as the star goes away from equilibrium, the rates change dramatically. We also show that this is a function of the age of the star. So the solid lines are for a relatively young neutron star, only 1,000 years old. The dotted ones are for an older star at 1,000,000 years. And obviously the younger star, which is hotter, the curves aren't quite as steep. And that's because the Fermi surfaces are more smeared out already in equilibrium. Okay. So we've seen that there's a very strong dependence on the deviation from equilibrium and on the temperature. What I haven't talked about yet is these blue curves here, because that is a process that, to the best of our knowledge, has not been discussed before, and that is muon diffusion. So if the star finds itself in a situation where it needs to get rid of muons, then one of the possibilities it has is for those muons to diffuse outside into a region where they can decay. In a star in equilibrium, that's forbidden. So the muons sit in the very inner core and they can't decay simply because there's no final states available. All the electron quantum states are occupied, and so the muon has nothing that it can decay into. However, one can show that just based on mean free path arguments, muons can diffuse over order kilometer distances, so over order the radius of a neutron star, over timescales that are maybe order years. So muons can actually leave the star very relatively efficiently if there is a thermodynamic reason for them to do so. And if they diffuse outward, then they at some point they pass the core crust boundary and they suddenly find themselves in a region where their decays are no longer polyblocked. And so the muons will simply decay, leaving behind an electron. So in a sense, this is an efficient process for a neutron star that needs to get rid of muons, but not so much of electrons. For instance, if the star needs to get rid of more muons than electrons, then this is a process that can happen. And we think that this is something that hasn't been realized before. It remains to be seen of how much practical relevance this is really in reality, because for most of the processes that we could think about, so spin down, accretion, B-field expulsion, the deviation from equilibrium goes in the opposite direction. So the star needs to create muons rather than get rid of muons. The only situation we could think about where the star actually wants to get rid of muons is tidal deformation, but the tidal deformations that are needed for this to really be relevant, they only happen in very, very tight binaries, basically binary systems that are only a very short time away from actually merging. So it's not clear how many processes there are in reality where this muon diffusion and decay can really play a role. But since we are sure we haven't thought about all the possibilities of what can drive a neutron star out of equilibrium, we are still presenting it because maybe one of you, maybe someone has an idea for where this could actually be relevant. So let me briefly stop here to make a somewhat more technical comment on how we actually go about this. This is nothing we really invented. This is essentially the calculation that you can find in the literature for calculating these Urca rates, originally due to Freeman and Maxwell, and there were a number of very useful papers and reviews later on. So the basic strategy for doing these calculations is, well, obviously you start with the Feynman rules, but given that this is a 2 to 4 process, you end up with a lot of integrals. And the integrals are not at all trivial, in particular because there's not only the terms that come from the Feynman rules, but there's also the various Pauli blocking factors that need to be taken into account. So the first step one typically does is one simplifies the nuclear matrix element, so the part of the amplitude that really describes the behavior of the hadrons. So this is somehow parameterized in a phenomenological way. Then one neglects the angular dependence of the matrix elements. This greatly simplifies the phase space integrals because now basically the matrix element and the phase space integral factorize to some extent. The nucleons can be treated as non-relativistic. That's a very good approximation. And perhaps the most important one is to use the fact that all the momenta are close to the respective Fermi surfaces of the various species. That's just a reflection of the fact that we are dealing with a cold neutron star. If we wanted to do that calculation for a neutron star that's only a few seconds old, then this would not be a good approximation. But for old and cold neutron stars, basically old here means more than a few seconds old, that is in fact a good approximation. Now with all these approximations, it's possible to first carry out the angular integrals and then the energy integrals, at least if one doesn't shy away from doing a complex contour integration a couple of times. So that's basically the technical steps that were taken to derive these curves here. Okay. Now, the title of this talk was Neutrinos from Neutron Stars, so let's finally really talk about the neutrinos. First, from the regular modified Urca processes in equilibrium. So for a neutron star in equilibrium at a temperature of 100 keV, which is I forgot what age exactly that corresponds to, maybe 1,000 years, maybe 10,000 years. I'm not entirely sure. But at that temperature, a typical neutron star can be expected to emit a neutrino flux of an intensity of 10 to the 22 erg per cubic centimeter per second. So integrated over the neutron star, that's ordered 10 to the 41 ergs per second. And if we imagine that neutron star is 10 kiloparsec away, then we end up with a flux at Earth of 38 per square centimeter per second. So that's already a relatively large flux. However, it's at an energy where neutrino detection is really extremely difficult. So it's highly unrealistic for that flux to be detected. Okay, but it's there. It arrives at Earth from all the neutron stars in the galaxy. There's a fair number of these low energy neutrinos that should get to us. For comparison, for instance, the flux of the diffuse supernova neutrino background is less than that, but of course it's at higher energy, so it's easier to detect. Of very great interest for detection could be this muon diffusion and decay process, if it actually happened in realistic systems. And that's because these would be neutrinos with an energy of order 10 MeV. Remember, the muons are now decaying in a region where their decays are not Pauli blocked. So they are basically decaying as free or almost free muons. So the neutrino energy is of order 1/3 of the muon mass, so order tens of MeV. So that's a very easily detectable neutrino energy. So let's make an estimate. A typical neutron star contains of order 10 to the 56 muons. So if we assume that 1 per mil of those muons are lost over a time scale of 1 gigayear, then the flux at Earth from that single neutron star would be 10 to the minus 10 square centimeters per second, which is very low. So the current limit in that energy range is 1 per square centimeter per second. And I find that already pretty amazing. Remember, these are neutrinos, so these have extremely small detection cross sections. And yet the detectors that we have are now so big that they can set a limit of order 1 neutrino per square centimeter per second already. But of course, 10 to the minus 10 is far out of reach. So the only situation we could imagine where this could possibly be detectable is if something was happening to all the neutron stars in the Milky Way at the same time that would make them lose muons all at the same time, but we are not of any mechanism that achieves that. I see a hand by Sanjay. Please go ahead.
Yeah, I don't know whether we're expected to ask questions during the talk or at the end. I can wait till the end if you have.
For me, it's fine if you ask now.
Okay, so I just want to understand this 10 MeV number. Where does this come from? Because the muon is diffusing, and it is going to get to a place where decay becomes energetically possible, but that could happen with a much smaller energy than 10 MeV. Because you're just opening up the phase space and then it's going to start coming up. So I want to understand where is this 10 MeV coming from?
The thing is that the phase space opens up really very quickly. So we were very skeptical about this too. So we ran a simulation. What we basically did is we took a neutron star from solving the TOV equations. We took the thermal properties of the neutron star at a given age from a neutron star cooling simulation. And then we had a muon do a random walk through this neutron star, and in each step of the random walk, we checked if it gets absorbed, if it decays, or if it just scatters. And we did this for various step sizes, and we saw in the end that as we decreased the step size, the rate at which the muons decay remained constant. And so what we think is happening, or what we see happening in the simulation, is because the density drops so rapidly at the core crust boundary, the muon almost instantaneously finds itself in a region where its decay is not blocked.
Okay, thanks.
Okay. But yeah, the practical relevance of this is highly questionable. For instance, if this spin down line here, if neutron stars spinning down, if that was on the opposite side, so if they were decreasing their muon abundance rather than increasing it, then this could be of relevance. But yeah, the sign here is the other one. Okay, so this brings me to the second part of my talk, where I want to talk about a situation in which neutron stars can also emit neutrinos, and in that case, it may actually be more easily detectable. And that situation is a so-called common envelope system. So here's a very complicated diagram that is meant to illustrate what common envelope systems are and why they are important. And the first take-home message from this diagram is it's obviously not easy. But so what a common envelope system is, it's a binary system of a compact star and a regular star in which the compact star at some point enters the envelope of the other star. So for a while, the compact object, so the neutron star, is propagating basically inside another star. And one of the reasons that this is relevant is because this is one of the main formation channels for many systems of great astrophysical importance, various kinds of X-ray binaries, and most notably, common envelope evolution is conjectured to be crucial for forming the tight binaries that we see merging in LIGO, Virgo, and Kagra. So what this diagram here is, this is from a review article by Ivanova et al. From 2012, which shows various possible evolution sequences of a binary star system, all of them involving common envelope evolution at some point, and all of them involving different outcomes. So it uses a lot of acronyms, so I've tried to explain those acronyms. So all the evolution channels here start with a 0H main sequence star. And at some point, these stars are presumed to experience Roche lobe overflow. So there's a difference in size between the two stars. One of them is accreting from the other. And at some point, the Roche lobe overflows, and at that point, a common envelope forms around the two cores. Let's see, which one should we go through? Let's go through the one on the very right-hand side. So here you start with two 0H main sequence stars. There's a first phase of Roche lobe overflow, after which one of the stars undergoes a supernova. So now you have one neutron star and one regular star. That's supposed to be forming a high mass X-ray binary. Then another common envelope phase happens when now the other star engulfs the neutron star. So now the neutron star is traveling inside the envelope of its companion star. And at some point, the companion star also turns into a neutron star. And now you have a tight neutron star binary system, a potential gravitational wave source. And the other evolution channels here, they lead to other interesting systems. But the phase that I'm most interested in for the purposes of this talk is this one down here. So the common envelope phase, where the compact object is a neutron star propagating, traveling inside the envelope of a regular star. And the reason I'm interested in this is because when this happens, the accretion rate onto the neutron star can be quite enormous. There is some debate in the literature on how big it can be. There is, I would say, most of the papers on the topic argue that the accretion rate is far exceeding the Eddington limit. Some papers argue that it can't exceed the Eddington limit. And I think the problem is that people have run simulations in which they artificially impose the Eddington limit and they get a consistent outcome. And there's people who have not imposed it and they get a consistent outcome as well. So it seems that evolution sub-Eddington and super-Eddington is both possible. The question is, no one really understands how the system would go from sub-Eddington to super-Eddington accretion. There are some ideas, but none of them are fully developed and fully understood. But in most of the literature, there is the assumption that the accretion rate can be large, up to 0.1 solar mass per year, to give you a number. But we are not entirely sure whether that's the case. It could also be much smaller. But let's take the idea, let's assume for the moment that it can be this large. So let's assume we have this neutron star sitting here inside the envelope of its companion, and it's accreting material at an enormous rate. Well, not for too long, because if it accretes at 0.1 solar mass per year, then it really disrupts the companion star. So typically it is simulations find that this phase lasts for maybe a couple of months, and then it's over. Once again, there's some debate on what exactly ends it and how exactly it ends. One possibility is ejection of the envelope from the system. But while this accretion is happening, obviously there's a lot of gravitational energy being released. And the point is that the only cooling channel the system has at this point is via neutrinos. That's because in the super-Eddington regime, the accretion flow is so rapid that radiation basically gets dragged inside along with the flow. So the infall speed is faster than the speed at which radiation diffuses outward, and that way radiation cannot act as an efficient cooling channel. Neutrinos, however, can. So if the accretion rate is that fast, then what will happen is the infalling matter heats up to the point where neutrino emission sets in, and then from that point on, it will radiate off energy into neutrinos. And those neutrinos could lead to an observable flux. There's, of course, a caveat, and the caveat is the rate at which these common envelope events happen. Obviously, to have a common envelope event, you first need a neutron star, and the rate at which neutron stars are formed in the Milky Way is the core collapse supernova rate in the Milky Way, or maybe it's less than the core collapse supernova rate. And not every neutron star undergoes common envelope at some point in its life. So the rate of common envelope events is certainly less than the core collapse supernova rate. The very rough estimate that one can come up with is that common envelope events should happen maybe between once every 10,000 years to once every 100 years. So it's not guaranteed that one of them will happen during our lifetime, but it's also not completely impossible. And therefore, we think it could be a good idea to look for those neutrino signals. So let's talk about those neutrino signals a little further. This is from a calculation I did together with Ivan Esteban and John Beacom. What's shown here is on the horizontal axis, the visible energy in inverse beta decay, so effectively a positron energy from a neutrino interaction. The vertical axis is the number of events per energy bin in the current configuration of the Super Kamiokande detector. I see a question by Lucas. Please go ahead.
Hi, Joachim.
Hi.
Actually, more of us sitting
Yeah,
on UCSD, and George has a
the
question.
crew at UC San Diego is watching your talk. Joachim, it's a very nice talk. So
Thanks.
just a question on that issue of the rate less than the core collapse supernova rate.
Yeah.
Well, just wondering, I mean, if I think about it, I don't really need the evolution scenario you showed. I could think of a reservoir of neutron stars, saying that in a globular cluster, some dense environment where you have mass segregation, where you have neutron stars capturing other stars. So have you thought about that?
Only very tangentially. So this estimate rate less than the core collapse supernova rate is basically assuming some sort of steady state situation. But I agree, of course, there could be situations where there are bursts of common envelope events for instance, in an environment like the one you propose. My main point here was we really don't know what the rate is. We are pretty sure it's relatively low, but we don't know exactly how low it is. On the other hand, we're also pretty sure that it's not so low that it's totally uninteresting to look for it.
Very nice. Thank you.
Thanks a lot for the question and the comment. Right, so coming back to this event spectrum here. So this is the current Super Kamiokande detector with a low concentration of gadolinium inside the detector. For those of you not so familiar with those detectors, a Super Kamiokande is a Water-Cherenkov detector. So it contains a lot of free protons. And the main neutrino detection reaction is inverse beta decay. So electron antineutrino plus proton going to a neutron plus a positron. The positron energy is seen via its Cherenkov light. And to enhance the detection efficiency, gadolinium helps because gadolinium very efficiently captures neutrons. And when it captures a neutron, it emits a several MeV gamma ray that is also detectable. And by this double coincidence between the positron and the gamma ray from neutron capture, one can very efficiently reconstruct these events. Now, at the moment, the concentration of gadolinium in Super Kamiokande is fairly low. There are plans for increasing that concentration, and that would then, of course, make this more easily detectable. And also in future detectors like Hyper Kamiokande, obviously, just because they are bigger, the rate would also be larger. But this is what we can do at the moment. And as you can see, for this system here, which if I remember correctly, was for a neutron star at 3 kiloparsec distance, the expected event rate from such a common envelope system is far above the backgrounds. So once it happens, detection should be fairly easy. And in fact, that is true not only at 3 kiloparsec, that is true essentially throughout the galaxy. So that's shown here. The horizontal axis here on these plots is the distance to the system. And the vertical axis is meant to show how likely it is that, it shows how well we cover the galaxy. So these white curves here, they show as a function of distance what fraction of the Milky Way stars are located within that distance. So obviously at order 10 kiloparsec or so, that curve levels out, because if we're able to look beyond 10 kiloparsec, then we are basically seeing the whole Milky Way. And the different colored bands here, they show the reach of different current and future neutrino detectors. The one I showed you before, Super Kamiokande with a low concentration of gadolinium, is this purple curve here in the upper plot. The yellow curve here to the left, that is Super Chi archival data without gadolinium. So maybe such a common envelope event is already there on tape. The current analysis would not have picked it up, but it's possible that it's already in the data. And yeah, then future detectors like Juno, Super K with more gadolinium, or maybe even a hypothetical Hyper Kamiokande with gadolinium could, of course, do better. On the bottom, we show the same not for antineutrinos, but for neutrinos. That's the domain of Dune, for instance. So for Dune, the distance reach is not quite as large simply because the detector is smaller. But the unique advantage that Dune has is because it would see these events in neutrino electron scattering, it has some directionality. So it's able to some extent to point back towards the source. Whereas with inverse beta decay, that's basically impossible. So the take-home message here is there is probably a new source of astrophysical neutrinos out there. We already have the tools to look for it, it's probably rare, but it's not so rare that we shouldn't be looking for it. Because if we detect it, I think what we could learn from such detection would be quite dramatic. First of all, it would be the first ever detection of common envelope events in the first place. These are conjectured to exist, but none of them have been observed directly. So it would be a first detection. It would tell us something about what's happening inside. For instance, it would answer the question whether or not the accretion rate is super Eddington. It would tell us something about the time scales of the event. And then once we've identified it, then maybe this would also help us to detect it also with, say, optical telescopes or other electromagnetic telescopes, and perhaps find some characteristic signatures in which such events, such common envelope events, would also show up in the electromagnetic spectrum. And that in turn might then help us to also detect them electromagnetically in the future. So I think there's a lot to be gained here. So especially since we have the instruments already, it's certainly something that, in my opinion, may be worth looking for. Okay, that brings me to the end of my talk. And I'd like to thank you for your attention, and I'm happy to answer more questions.
Thank you, Joachim, for the very nice talk. Sorry, I was late in the beginning.
No worries.
Yeah, maybe people can ask their hand.
Yeah,
Okay,
I see
see a hand from
Susan already.
Susan, can you unmute yourself, please?
Oh, thank you very much. Thank you for that lovely talk. I have
Thanks, Susan.
maybe a question and a comment. My question concerns slide 15, and it's particularly in regards to the 15.
Yeah.
Where, I'm sorry, it's the one with has the common envelope picture and how you start. That's right, the counting of the stars. So my question is this: I mean, I sort of see what you mean by the counting, because it's about 8 kiloparsecs from where we are to the galactic center. But I thought there was evidence to think that the actual physical distribution of neutron stars was not comparable to that of ordinary stars, that their scale height was much higher than the usual thin disk that we associate with the Milky Way. And therefore, although maybe on broad order one counting, this is all right, what do you think? I mean, I thought there was some simulations and maybe comparisons, maybe with Gaia, details of which I do not know, in which maybe some of this question I have can be refined, and I was wondering what you could say about it.
So the reason we used the distribution of just regular stars as a proxy here is that most of the stars in the Milky Way are located close to the galactic center. And so also the neutron stars will mostly be located close to the galactic center. And because that is already 8.5 kiloparsec away along the plane, then the scale height, for instance, so how far they are out of the plane, I don't think it will affect us that much. Once we have a reach that goes out to 8.5, 9, 10 kiloparsec or so, then going a little bit up and down won't change the line of sight distance that dramatically. And given that also our estimates for the sensitivity reach of the instruments, I would say is definitely not percent level accurate. We felt that this was an accurate enough proxy, but I agree that one can of course do better by taking into account the actual distribution of neutron stars, not of ordinary stars.
Thank you very much for that. If I may, just very quickly, I would just like to point out that I have work of my own on, how neutron stars can be brought out of equilibrium, chemical and thermal equilibrium by apparent baryon number violation. And we've studied this possibility of exotic neutron dart decays and how the limits can be set on energy loss constraints from pulsar binary lengthening, non-observation, or a lack of anomalous energy loss. So that would asking for additional examples, and I just wanted to point that out.
So that would be processes beyond the standard model, right?
Oh yes, oh yes.
Yeah.
I mean, yes, it's true.
Yeah.
But
yeah, that's indeed a very interesting direction and a very interesting comment. So thanks a lot. That is something we have not really thought about in this project. But so both Toby and I are coming from the BSM side. So we obviously always had BSM physics a little bit in the back of our minds, but we decided to first talk about the standard model. But I definitely have read your papers on this, because I think this can indeed be quite interesting.
Oh, thank you very much. I just wanted to bring it to your attention. And in
Thanks
fact,
a lot, Susan.
because this issue of baryon decay might be particularly important in the core of the star, in our analysis, we actually use relativistic mean field theory. So it's, again, a little bit different in detail. I just wanted to say, thank you so much.
That's very useful. Thanks a lot, Susan.
Thanks.
Thanks, Susan. Lucas, can you please unmute yourself?
Hi, this is Anna, actually. I wanted to
Hi.
ask about part of your talk. So I think maybe you said it, or I just maybe didn't get. When the muons, there is mean free path of muons that is letting them diffuse on order of year.
Yeah.
And you disturb the equilibrium by some process so that the equilibrium distribution is changing. So my thought was that the equation of state would somehow respond on a much faster timescale than a year, so that the muons couldn't really diffuse.
So the reasons that in a star in equilibrium the muons can't diffuse outward is that essentially once a muon has diffused outward a little bit, there's an electromagnetic charge imbalance that pulls it back. So the only way to overcome this is if the muon goes out, decays into an electron, and the electron moves back inside. And in a star in equilibrium, this is energetically unfavorable. So it won't happen, because then you're taking away a muon from the top of the muon Fermi sea and adding an electron at the top of the electron Fermi sea. So overall, you've put more energy into the system, and you've brought the two lepton Fermi levels out of equilibrium. So normally in beta equilibrium, the electron Fermi energy and the muon Fermi energy are equal, and then you are disrupting this. So that's why we are insisting so much on the out of equilibrium situation. We need the star to actually want to get rid of muons. Ideally, to get rid of more muons than it gets rid of electrons, because that's the only situation that we can imagine where there is not an electromagnetic barrier building up that prevents the muons going out and the electrons from the decay going back inside. Now, I'm not entirely sure I understand what you mean by the equation of state responding, because the equation of state, in a sense, is just an assumption of how how the different particle species in the star interact with one another. So I would say the equation of state is fixed, but of course, within the equation of state, there's variables like the core density or so, which change, and we think that it is those changes that drive the change in the particle abundances that the star then somehow has to respond to, and the star has to do something to go back into equilibrium in spite of the changed boundary conditions. So the way I look at this is, I would say, we have a neutron star and we are changing the external boundary conditions. So that means now the new equilibrium configuration is different. But the star, of course, is not in that new equilibrium configuration yet. And then we're asking the question, how does it get there? How does it destroy particles or form new particles to realize the equilibrium situation that the equation of state dictates?
Yeah. I think I just thought that the new equilibrium would be somehow reached faster than the timescale which muons diffuse.
Well, to our understanding, the only way in which you can make or destroy muons is either via Urca processes or via muon diffusion and decay. So if Urca is possible, if Urca is fast enough, then that is certainly what will happen. But if you look at this plot here, there is a certain regime where muon decay and diffusion is much faster than muon destruction via modified or direct Urca processes. And that's why we think there could be a situation where muon diffusion and decay actually wins.
Okay,
so the requirement, yeah.
That answers the question. Yeah, thank you.
Yeah. Thanks for the question.
Sanjay, can you please unmute yourself?
San Diego here. This is George. So,
Hi, George.
great talk, Joachim. So, great food for thought. Back on this issue of common envelope evolution. So people have considered this before, but in the context of stable objects. I'm thinking of like Thorne-Zitkov objects with a neutron star of a distended envelope. And there, of course, it's hydrogen burning, hot hydrogen burning that kind of stabilizes things at a lower temperature and at a fusion rate. So I'm just wondering, I mean, if I remember correctly, I mean, the formation channel for TZOs was supposed to be common envelope evolution.
Indeed.
And can you comment on that?
Yeah, my main comment is that there is a lot of debate in the literature. So I agree that TZOs, for those who are not familiar with the term, a TZO is basically a star that has a neutron star at its core, but has a regular stellar envelope on the outside and is doing nuclear fusion on the outside as usual. So TZOs are one of the possible endpoints of common envelope evolution, and there is debate in the literature on how likely it is to form a TZO as opposed to ejecting the envelope. For instance, for the formation of the binaries that we detect in gravitational waves, it's preferable that the envelope is ejected. So you now have two compact objects that orbit each other at a small distance. Now, you mentioned that TZOs, there's obviously a stable solution where the hydrodynamic pressure keeps it stable, so prevents the star from just collapsing onto the compact object at its core. And I'm not entirely sure we understand how the star gets from one regime to the other. So there is simulations of common envelope systems in which you see these super Eddington rates, and there are solutions for TZOs that show that they can be stable, but I'm not sure anyone has really calculated how to get from one stage to the other. The only simulations I'm aware of, or the only calculations I'm aware of, that really simulate this evolution in a consistent way throughout the process, those are simulations where the Eddington limit has been put in by hand. And so it's...
Very good. I would just say that, you know, the essence of the TCO is that you're doing hot hydrogen burning, maybe even RP product. So you would, if you ever could observe the ejective, you knew the direction of this thing, for example, it would look, the synthesis would look weird. It would be kind of iron. It wouldn't make sense. Anyway, very
I didn't hear the last sentence, George.
Oh, just saying that the nucleosynthesis from hot hydrogen burning, from breaking out of hot CNO cycle and making the RP process, for example, would be, it would look strange. It would be like nothing else. It would look like iron. It would look more like a supernova problem.
Yeah, my understanding is that there is a few papers that have tried of people who have tried to look for TZOs by looking at certain signatures in the spectra of the stars, the occurrence or non-occurrence of certain elements. But all of this seems to be highly controversial. So there's a few claims for the detection of a TZO, then there's other papers arguing that no, this can't be a TZO and there can be a more mundane explanation for it. So this all seems to be very much in flux. So it would be really great to observe this in neutrinos, because I think if we had it in neutrinos, this would probably really be a smoking gun. I can't imagine any other process that leads to such a signal that is transient over a timescale of a couple of months, has that kind of flux. Yeah, but it seems there's a lot of questions that still need to be answered, and maybe neutrinos can be one piece in the puzzle.
Very nice. Thank you, Joachim.
Thanks, George.
Sanjay, can you please unmute yourself?
Yeah, thanks, Joachim. That was a really interesting talk. Lots of interesting ideas being explored here. I have a question about the accretion driven neutrino processes. What's the spectrum of these processes? What's the spectrum of the neutrinos? What are the underlying processes that are generating the neutrinos?
So the spectrum is more or less a thermal spectrum, and the underlying processes are plasmon decays and E plus E minus annihilation.
Okay, so the accretion just creates a hot plasma,
Yeah.
relatively low density, that the neutrino mean free paths are large. Every neutrino that's produced just leaves the system.
Yeah, so we checked that. So the neutrino mean free paths are not an issue. Once you've made a neutrino, it can easily get out of the system.
And so when you say thermal, what's the temperature that you see in the spectrum?
Order an MeV.
Okay.
So a little bit above an MeV. So the main backgrounds that we have to contend with are in fact from just radioactivity in the detector.
I see. Okay.
Or in the surroundings of the detector.
Okay, so I vaguely recall a paper by Chuck Horowitz and some collaborators where they were looking at accretion and speculating that accretion could produce pions, and that these pions can then decay to produce much higher energy neutrinos. Have you thought about whether production of pions, because I guess these nucleons that are hitting the neutron star are coming in at around 200 MeV per nucleon, whether that could produce a higher non-thermal component to the neutrino spectrum?
I remember we had discussions about pions. I don't remember why we concluded they are not important.
Yeah, just a comment. I think there's a paper about pion production and accretion by Chuck Horowitz.
Yeah, I remember we discussed this. I definitely remember we discussed pions. I'm just trying to remember what the argument was why they are not important. Maybe the reason is, so the infalling material, it forms this hot shell of matter around the neutron star because it can't be incorporated into the star at the rate at which it falls in.
Yeah, okay.
So
That answers the question. Okay, that makes sense. So
I guess, yeah.
Okay, all right, I got it. Thanks.
Sure.
Yeah. I think there are no further questions. Sorry, I think there is one more question by R. Mark Elvidge. Can you please unmute yourself?
Yes. This is kind of a generic question, but let's say if you had like a quark star versus a neutron star, how would that affect the muon emission rate and hence the neutrino rate? And could you use that to discriminate a quark star from a neutron star anyway?
So I don't have a definitive answer to that question. I'm thinking about how you would use it. I would be worried that so first of all, of course, we need a system where muon diffusion is important in the first place. But if we assume that we have a neutron star or quark star in such a configuration and we see the muons decaying, my worry would be that there's too many degeneracies with other unknowns in the equations of state and so on, that just observing the neutrino flux would not be enough to tell us about that, because those neutrinos, they are coming from the outer regions of the star when the muons have already left the most interesting region of the star. So the only point where information on the inner workings of the star could be encoded is in the diffusion time, and there I would be worried that there's too many degeneracies with, say, the exact process that drives it out of equilibrium and so on. So I'd be skeptical.
Thanks.
Yeah, thanks for the question.
There are no further questions. I have one question, sorry. So you said the common envelope system rate are lower than the core collapse supernova rate. So I just want to get a number. So it's 1 events per 100 years or 1 events per 1,000 years? I mean,
so the estimate we put in the paper is between 1 event every 10,000 years and 1 event every 100 years.
Okay.
But as we discussed previously, there can be situations where the rate can be enhanced, because what we've assumed is that somehow everything is in a steady state. But you could, for instance, imagine a lot of neutron stars ending up in a system where they very efficiently form common envelope systems, where they very efficiently form binaries. And then maybe the rate can even be larger than 1 per century. But I would consider that a rather optimistic case.
Okay. Okay. Again, thank you again, Joachim, for your very nice seminar. I don't see any more questions, so thank you again, and we will meet next week.
Yeah, thanks all of you for listening and for all the interesting discussion. Thanks a lot, everyone, and hope to see you soon.
Thank you.
Bye-bye.